So big question to me that I want to tell you about where I stand, first of all, is, right, is this Hubble constant tension new physics or systematics? Of course, that's, this is very germane to the subject of this conference, and thank you for the opportunity to speak here on this matter. And well, Sean Lee asked me, as an outsider from the distance ladder community, how does this all look to me? And as an outsider, which I don't do distance ladder work professionally, it's hard for me to be definitive about this question when the distance ladder community itself is divided. At the same time, Adam and the Shoes team make a very persuasive case that this is worth taking seriously. And it's given me and many others, I mean, you just heard a great talk from Tanvi, motivation to explore departures from lambda CDM. This has been a really fun exercise to go through. It's mostly served to give me an increased appreciation for what lambda CDM gets right, because it's hard it's hard to accommodate a higher Hubble constant and still get all these things we know about the universe from observations, still get them correct. It's pretty extraordinary what lambda CDM does, despite this issue that, right, we don't know what lambda is, we don't know what the CDM is. I find historical analogies useful for trying to think about where we are now. And so it's worth pointing out that in the 18th century, Newtonian gravity was a tremendous success. There's all these observations that it explained. It was even used to discover a new planet, right, Neptune. But that perihelion precession of Mercury was an important clue. So there's all these successes of the model and this one outlying thing. So it's an exciting possibility that we might be learning something here. And this possibility led me to do some thinking with Marius Milea that became this paper about 5 years ago, the Hubble Hunter's Guide, where we wrote, here we consider a variety of types of departures from lambda CDM that could, in principle, restore concordance among these data sets. And we explain why we find almost all of them unlikely to be successful. We single out the set of solutions that increase the expansion rate in the decade of scale factor expansion just prior to recombination as the least unlikely. So we still weren't enthusiastic about these solutions. These solutions are themselves tightly constrained by their impact on photon diffusion, on the gravitational driving of acoustic oscillations of the modes that begin oscillating during this epoch, modes that project onto angular scales that are very well measured. So, of course, we just heard a talk from Tanvi that was consistent with that. So these types of solutions are still obviously interesting to explore. But I want to tell you something about the barriers they face, about these acoustic dynamics, and then the implications for light relic-like models. So even though Tanvi and I didn't coordinate, we did a decent job of remaining complementary here. And then related to the light relics, this scaling transformation symmetry that with a couple collaborators we found in the Einstein-Boltzmann equations, and how we can think about alternative models and how they impact, how they're constrained by all the observables we have. Then I'm going to say a bit about some recent work on recombination, which has emerged as an interesting possible piece of the lambda CDM picture that might get modified to achieve concordance. And then I want to say something about things that are coming soon that bear on these questions from the South Pole Telescope. So let me begin talking about acoustic dynamics driven by decaying potentials. So here we have a universe with some spherical overdensity here, some spherical top hat overdensity. M is the mean mass you'd have in this region. Delta M is the positive fluctuation upwards. And we're looking at the gravitational potential here. R is some co-moving distance. A is the scale factor. And so the potential per unit mass is given by this. And if we evolve this forward due to expansion, but we don't transport any matter around, then at a later time we have this. We have that same mass in this expanded sphere. We have an expanded distance to our test particle, and so we have a decrease in this potential because that distance has increased. So so the potential decay is just from the expansion. Of course, we do have transport of matter, and that transport, if we're in a matter-dominated universe, is just right to boost that delta m so by one factor of the scale factor, and that exactly cancels this value of the scale factor down here. So as I'm sure you all know, right, that in a matter-dominated universe, free fall leads to transport that exactly balances the expansion to keep the potentials constant. And on the other hand, right, that's matter flowing in at free fall. If you have pressure support, that slows the transport, and so the gravitational potentials decay. And that decay has significant influences. And to talk about those influences on the dynamics, let me come back to talk about harmonic oscillators. The classical harmonic oscillator, we're going to do some simple physics with this. It's going to relate to the dynamics of the standing waves in the plasma. So here's a harmonic oscillator. Here's a harmonic oscillator under some tension from a weight. So this is perhaps for some of you an introduction to imperial units. Sorry about that. I have my 80-pound weight here. We're using inches here. Anyway, this is what I found on the internet. So here's the force-free equilibrium position. We add this weight, right? The force-free equilibrium position now is at 80. The equilibrium position is now down here because of the weight and the gravity that's here. If we displace this down by 3 inches here and let it go, then it would just oscillate here about this equilibrium with an amplitude of plus or minus 3 inches. All right, now what if during that oscillation it hits the lowest point here, 9 inches down, and the weight all of a sudden disappears. So I don't know, I just take the weight off of this out at here at the bottom. It's at rest here at the bottom. The weight disappears. The new equilibrium position is here, up at 0 inches. So now we have an amplitude of oscillation that instead of being plus or minus 3 inches, it's plus or minus 9 inches. Okay, so that's a boost. Due to that weight reduction at the low point of the oscillation, we have a boost of a factor of 3 in the oscillation amplitude. And if we remove none of the weight, right, then that's the oscillation amplitude boost factor of 1. Nothing changes. And then there's some smooth interpolation in between these as we consider reducing that weight by various percentage points. Now, to talk about this in the cosmological context, it helps to flip this. It actually helps to flip this upside down. So we're just flipping that whole arrangement upside down. Gravity's still pointing down. And if we have this 80-pound weight and gravity's pointing down, then this is our new equilibrium position, 6 inches below the force-free equilibrium. And let's see. Let's imagine we start with the bottom weight here at rest. And if we don't change that weight, it's just going to, again, oscillate up and down with an amplitude of 3 inches. But let's look what happens when we're thinking about either the matter-dominated universe, where the gravitational potential doesn't change, right? So that weight doesn't change. Then we stay with that small range of amplitude of oscillation. But in a radiation-dominated universe, just as the fluid compresses, so gravity is the more important force first for adiabatic perturbations. The fluid compresses into a potential well. And just as it's reaching maximal compression, that potential has almost entirely disappeared. Right? So that's like the weight being lifted off the spring. And so we get this resonant driving of the amplitude of the acoustic oscillations. And this is a huge effect in the CMB power spectrum. So let's turn to looking at the CMB power spectrum. Here's the temperature power spectrum in lambda CDM. And before talking about the impact of this resonant driving effect, it's helpful to remove another huge effect, which is photon diffusion. So photons will diffuse out of hot spots into cold spots, and out of cold spots into hot spots before they last scatter, and so that suppresses fluctuations below that free streaming length, and we see the impact of that suppression here. If there were no photon diffusion, the power spectrum would look a lot more like this. So this is a huge L-dependent effect, which, by the way, lambda CDM gets right. More on that later. But it helps to take this out, and what we're looking at now. I talked about matter domination and radiation domination. This is actually the dividing point between modes that enter after matter radiation equality and modes that enter before matter radiation equality. So it's really right here on the far left-hand side of this plot. This is how we get to probe it. We don't have anything completely in the matter-dominated regime, but we get to observe this transition to some degree, which is really helpful in terms of constraining things. So here's the percent. This is like our percentage of weight that we reduce. This is percentage of energy density in relativistic matter when the oscillations begin, when these modes cross the horizon that project into a given value of L. And this is this oscillation boost factor, or its square, since this is the power spectrum. This is what Hu and White, who talked about this in their 1997 paper, call the potential envelope. They also refer to this as radiation driving. And just to orient you, if we set the scale factor to 1 at recombination, this is like, this is basically 1 over the scale factor then. This is the scale factor relative to recombination. So these are the epochs that we're probing in terms of scale factor. And this is all really well measured, right? So here's the Planck data as well as ACT-DR4 and our initial results from SPT3G, just plotted here in every L range. What are the best current measurements? So this is extraordinarily well measured, and this is a huge effect, and it greatly constrains things. And the potential decay also gives rise to the early ISW effect that Tanvi was emphasizing in terms of its constraints on early dark energy. But this whole range makes it challenging to put some new ingredient into the model and not manage to mess things up. It's a significant constraint on these early dark energy models. I want to look at implications for light relics. And I'm going to lead you through constraints on light relics as we complicate the model some to evade various effects. All right, so we have here, this is using Planck plus pre-DESI BAO data, and the dark black here is the lambda CDM result, so with NF at 3.044. And then if we let NF be free, and in particular have it be a free streaming component, then this spreads out like this. And a major thing that's restricting this from spreading out further is this photon diffusion effect. We can add helium, which also affects the photon diffusion scale because it affects the number density of free electrons, and get rid of that photon diffusion as a constraining effect. And this spreads out a little bit more. And what's constraining us here, that we're changing the ratio of free streaming relativistic particles to fluid relativistic particles. So the plasma is, of course, behaving as a fluid. These free streaming particles are freely streaming, so they free stream out of overdensities much more rapidly than the sound waves can carry stuff out of an overdensity. And that affects how gravitational potentials evolve. And so that difference in how gravitational potentials evolve has an impact on the evolution of the standing waves in the plasma and leads to these constraints. We can take care of that effect by letting by actually having light relics that are fluid, that are behaving like a fluid, so we can preserve that ratio. There are directions in the parameter space that preserve that ratio of fluid to free streaming radiation, and that opens things up a bit more. It's still constrained, though. So this is, anyway, this was a puzzle to us for a while. And, well, I guess I can tell you now why it's happening. As you're increasing NF, in order to keep this radiation driving envelope, this potential envelope, from changing too much, you've also got to boost up the amount of dark matter. So that's keeping this ratio of radiation to matter fixed, and which is really critically important to how these potentials decay and drive the acoustic oscillations. So as you're increasing NF in these model spaces, you have to increase the matter density. And for other effects, you've got the baryon density pinned down, so you're increasing the matter to baryon ratio. So you're changing the fraction of matter that's pressure supported. That also influences how gravitational potentials evolve and influences the driving of the plasma. So that's the remaining effect here that is leaving us constrained here in the values of H naught that are compatible with the data. So now I want to talk about something that our investigation of light relics and trying to figure out that story I just told you led us to, which is this scaling transformation symmetry in the Einstein-Boltzmann equations, and then this a rate ratio perspective as a way of thinking about the relationship between theoretical quantities and the observables that they impact. So let me just introduce what this transformation is. It's we call it this FFAT scaling is for free fall, amplitude, and Thomson rate scaling. So here is the scaling transformation. If we take the free fall rate for each species, where I is neutrinos, photons, dark matter, anything that's in there, scale it up by some value lambda. And we do that with the Thomson scattering rate as well, and we do that with the amplitude of the primordial power spectrum. Then all these observables are invariant under this transformation. This is just a result of the fact that these are all the dimensionful coefficients in the equations of motion, and it's basically dimensional analysis plus the scale-free initial conditions that allow us to do this. All right, and that's basically what's being said here. These are all the dimensional coefficients in the relevant equations. Of course, the Fourier wave numbers included there too. And because you need to scale up the Fourier wave numbers, you correct for that with this transformation of the amplitude of the scalar power spectrum. So note that this also includes, importantly, the expansion rate. That's a very important rate in the problem. And right, these are the two people that were critical to getting this done. Fantastic graduate student at UC Davis, fantastic collaborator of mine, Francis Jan Cyr-Racine. And another, I realized recently that this could also be Faye, Francis Jan, and this other guy. Having discovered this symmetry, we looked for a cosmological model in which we could implement it. to take advantage of this, right? Because if you can scale all these things up, not change the observables, well, you're scaling up all these rates, including the Hubble rate, right? So that's an interesting thing to do. And we found that if, in addition to freeing up helium, we had what's called a mirror world dark sector, so a copy of the standard model of particle physics as the dark sector, then we can effectively implement this scaling transformation in this model space. And here are the constraints that come out, right? So this cutoff here at high value of the Hubble constant is due to a prior we put in. We just weren't interested in exploring higher than that. And this is because this sensitivity here is because there are important rates that we didn't scale. So I lied a little bit before in saying those are all the important rates. There's also, missing were the atomic reaction rates that are important for determining how recombination proceeds. Those don't get scaled, and their effect leads to this sensitivity here to the value of the Hubble constant. So pretty mild effect. So this looks like a potential solution to the Hubble constant, but there are some problems. Namely, we know how much, we scale the Thomson rate there by letting the helium be free. So if you have less helium at fixed baryon fraction, then you're basically giving free electrons up. And so you're increasing the free electron density. And that's how we increase the Thomson scattering rate. And we prefer, right, this is following the scaling solution here, these contours. And the high values of the Hubble constant are up here. And so to get a high value of the Hubble constant, we need low values of helium. And there are people who have gone out and measured how much helium there is in the universe, and there's much less helium than we want. And then there's also the fact that we've introduced these light relics into the problem, and we have not scaled the nuclear reaction rates that control Big Bang nucleosynthesis. And so, the BBN constraints say we got to be down here. So that's the state of things. Right now, this raises more questions, I think, than it answers. It's unclear whether this is a path to the Hubble constant solution or not. I doubt it, but it has been something that's helped us understand analytically where our constraints come from. And it's also led us to this rate ratio perspective, where we can think about ratios of rates, right? If all observables are unaffected by the scaling up of all rates, then consistent with that is if you have a particular rate ratio and you change it, right, you're going to be violating that scaling, and there's some observational consequence attached to that. So I should include in here perhaps the 0th order thing, this density of matter to radiation, which really affects that radiation driving. So that's an important rate ratio, square root of rho matter over square root of rho radiation. And then there are these other ones here, which, let's see, I won't bother going through all of them, but this is the new one we found and understood as really important to constraints on light relics, this ratio of pressureless matter to pressure-full matter to pressureless matter just prior to recombination. So speaking of recombination, let's speak about recombination. So from the Hubble Hunter's Guide, another excerpt from that paper, I wrote, changes to the physics of recombination sufficient to change the sound horizon by about 7% will wreak havoc on the shape of the damping tail. So this is a reason that we thought it was more likely to be adding stuff in to increase the expansion rate, to bring down the sound horizon, rather than playing around with recombination, because the recombination calculation in lambda CDM really works so well to get the damping tail. I thought it was unlikely, right? It seems unlikely that new physics alters the sound horizon by changing recombination while having an acceptably small impact on the shape of the CMB damping tail. Well, on the other hand, here's a paper 3 years later, this H-naught Olympics paper, which I'm sure a lot of you are familiar with. And here are these models trying to move this, if you like, this lambda CDM constraint on the peak brightness of supernovae over to where Cepheid calibrated supernova peak brightness is. And this is another framing of the Hubble constant tension. And if you adjust these models, constrained by Planck plus BA plus supernovae, right? This is one little snapshot of how difficult it is to actually really strongly relieve this tension. And yet here's the gold medalist, right? Varying electron mass. What does that change the electron mass doing? It's changing recombination. So here's a model in which the electron mass is changing. So you're changing recombination, and it's the gold medalist in this competition. So given our interest in scaling up Thomson scattering rates for the FFAT scaling transformation and the failure of helium to provide a way to do that, and the success of these varying electron mass models, phenomenological success of these models, became interested in thinking about recombination and started talking with Ge and Chluba, and then my graduate student at UC Davis, Gabe Lynch. And we just first started asking ourselves, well, if we free up the ionization fraction, and then what do the data want, right? So what do the C and B data want? And I was actually surprised at how much freedom there was. I thought it would be more tightly constrained than it is, but some significant departures are definitely allowed. So that's the ionization fraction as a function of redshift, and then the visibility function here. And then, interestingly, low redshift data have a significant impact on this, because these changes have an impact on low redshift observables, and particularly ones that BAO is sensitive to, omega matter and this product of the baryon drag epoch times the Hubble constant. So that tightens that up significantly. And we had just finished a paper about this 2 days before the DESI data came out. And so we realized that these DESI data were interesting in this context, and wrote this paper. And let me lead you through that a bit. So first of all, this is omega matter H0 plane. This is the constraints from Planck given lambda CDM. And you can think of this as due to constraint on omega matter H squared from the radiation driving effect, and the combination of that with constraint on omega matter H cubed, which in lambda CDM correlates well with this angular size of the sound horizon. If we right, so omega matter H squared constant line is something like this, omega matter H cubed lines are something like this, and they intersect here. If we free up recombination, we lose that omega matter H cubed constraint, and so the constraints from Planck relax to this. Now, this model is lambda CDM except for recombination, and so from the BAO data, all we get out is omega matter and RD times H. And if we just look at that omega matter constraint, we see that it's coming in a bit low from DESI, and in this model space, that ends up boosting up the Hubble constant. Here's what we get from a joint fit. That's not all coming from omega matter. In fact, more of the influence is coming from the DESI inference of this product here, RD times H. They both go in the same direction of shifting up towards higher values of the Hubble constant, and the net result is H0 is 70 plus or minus 1.1. Of course, that brings the question is what physics could cause this, and one possibility, as far as we know, and this is still a subject of investigation, or one that I hope we'll be investigating soon, or others, is that this could be primordial magnetic fields. So, our best fit is ridiculous, right? It looks like this. Okay, that's not going to come out of a physical model, but we get a pretty good fit also from a smooth version of this, which is here, and that's not entirely different from what other people have found from primordial magnetic fields. So perhaps that can do this. What's happening is the magnetic fields are causing some clumping in the baryon density, and the denser regions are recombining earlier. And on average, there's an earlier recombination as well. So what to expect from SPT3G? This is work done by, a lot of it done by the people shown here, a lot of work as well from the whole South Pole Telescope collaboration. And so let me tell you something about what we're doing in SPT. So this is the third generation camera on the South Pole Telescope, this 10-meter dish at the South Pole. And we've spent 5 years drilling down during the austral winter on this patch here. One of our primary goals is to do delensing for BICEP and Keck. And then in the summer, we've observed these fields for 4 years now, which these are fields where we can avoid sun contamination, and as well as this yellow field over here. And right now, and just for some months now, with the beginning of the most recent austral winter, which we're in now, we're surveying this, all this other sky here, trying to get as much sky as we can from the South Pole, and while avoiding excessive amounts of galactic foregrounds. So what are we going to get from this? We call that combination of all this the extended 10K for 10,000 square degrees. That's a combination of all these fields. That really deep patch is the main survey. This is completed already. And this is a plot of signal to noise for polarization and lensing power spectrum versus multipole, and just comparing to Planck, right? So we make huge advances over Planck in measurement of the lensing power spectrum, and as well as the polarization power spectrum, even out here at intermediate L values, and definitely out here at higher L. And that's true for temperature. There's also gains in temperature as well. So here's the signal to noise in Planck for temperature, and for these two different 3G surveys. What do we get from this? Oh, well, one thing I want to emphasize is the lensing. Here is our lensing reconstruction noise for various surveys. The main survey is sufficiently deep that the quadratic estimator is no longer, it becomes significantly suboptimal. We have a Bayesian method to reconstruct the lensing potential instead, and that gains a significant reduction in noise here. This will be useful for delensing the BICEP Keck data. And then if we look at the forecasted error bars on the lensing power spectrum, this is going to be quite a constraint. This here, the red is our 10,000 square degree survey, and then we have here's ACT-DR6, which is already really impressive, and we're coming down below that. Here's SO baseline. So we'll be doing similar to the Simons Observatory baseline, and doing that a few years earlier. So how are we testing lambda CDM with this? Well, one way to think of it is that we're measuring signals that are quite complementary to those to come from Planck. And so we can infer lambda CDM parameters from those signals and compare with Planck, and that's a powerful test of lambda CDM. And so how well can we determine these parameters? Here's a figure of merit, which is telling us about the volume of the parameter space, the constrained parameter space relative to Planck, where going up here is getting better. This is 100 times smaller constraint from our data than from Planck. And this is how this is marching up over time from the survey data we have. We're somewhere about here. And we're currently analyzing data from these first 2 years and hope to have results out by the end of the year. Here are some forecasted error bars. This is TE, and here's a prediction from this modified recombination model. So photon diffusion becomes an even bigger effect out here, and we're sensitive to this. So we're actually going to be able to, this model is making predictions that we can test in the very near future. And let's see. So, right, we're analyzing these data now. And let me not say anything really too much about the methodology because I'm running out of time, and just show you some preliminary results for a reconstructed lensing power spectrum and the reconstructed unlensed EE power spectrum. So part of the estimation process here is we're jointly estimating the lensing band powers and the unlensed field band powers. Anyway, it's still fun after all these years to see new peaks emerging. We hope to be getting cosmology out of this soon. So to summarize, so barriers to high H0. While making model changes to boost H0, there are many rate ratios to try to keep fixed to avoid bad observable consequences. I think this is fundamentally important to why this has been so challenging from a theoretical perspective. Remember that H0 Olympics plot where all these different models are struggling to get over to the right. I think that anyway, I think that this is an answer to that question of why is this so hard to do. Radiation driving is a huge effect that light relics models can avoid changing, but in general, it's non-trivial to get right. I think it's in particular a challenge. It's one of the reasons that the upper limits on how much EDE was there were what they are, as we saw from Tanvi. Lambda CDM gets it right. It's impressive. It's a huge effect. Lambda CDM gets it right. Photon diffusion is also a huge L-dependent effect. Lambda CDM gets it right. I think that's important to take into consideration and not get too carried away about what you can do when you free up recombination. We'll see, though. Are we going to be pushed into having to free up something about recombination? Might this scaling eventually lead us to a solution? So far, it only raises more questions. And then, right, if significant alterations to recombination are actually acceptable to the CMB data and can possibly lead to concordance, right? And the DESI data for Tanvi emphasized how BAO and supernovae have been very constraining on types of solutions you can have to the Hubble constant. But these DESI data, if they hold up, they've kind of changed this to some degree, and there's actually some support for a higher Hubble constant. Big question, can we find a physical way to deliver this? And finally, right, we have these great data, great constraints coming from sp3G. Early recombination is something that we can test in the very near future. Okay, thank you very much.
So questions, comments? Yep.
Thank you. From a particle physics point of view, I wanted to know how you reconcile your change of NF with particle physics experiments who claim that NF equal rather 3.
Are you talking about from the width of the Z boson decay or
LHC?
I mean, you're talking about constraints on active neutrinos.
Anyhow, what is the mechanism that you use to meet NF?
So often in particle physics, particle physics models that lead to new light relics, people come up with these all the time, so I'm told, and then they can be thermally produced in the early universe, right? So if you have some theory that has some new stable light particle, you have to worry about, is this going to get produced in the early universe thermally, right? And so if so, then that could show up as a contribution to this ineffective, right?
So it's a running NF, is it?
Yeah, it's a relic. So yes, I'm sorry. I'm just talking about relic radiation, presumably thermally produced in the Big Bang. It wouldn't have to be thermally produced, but yes. So relic radiation from the Big Bang, dark radiation.
Leandros? So if you make a recombination occur earlier, of course you make RB smaller, and then for you increase.
A combination of what?
If you modify recombination, as you
Modified recombination. Yes. Okay.
you make it occur earlier.
Yeah.
You make RD smaller.
That's right.
And then you increase H naught.
Right.
So the H naught you have there is 70 plus or minus 1.1. What makes you not make it even earlier and then increase H naught even further? What is the constraint that you have to satisfy which limits you to 70 and doesn't allow you to go to 73.04?
Yeah. Great question. So we still have this constraint on, it comes back to these radiation driving effects. So you change the matter to radiation ratio, you're going to change where matter radiation equality is. You're going to shift that radiation boosting envelope, right? That acoustic oscillation boosting envelope. You're going to shift it in L if you change the matter to radiation ratio. And there's only so much tolerance for that. And we're not losing that constraint. So this is in fact a line, so this is going along a line of constant omega matter h squared. And, or nearly so. This is a line of constant omega matter h squared. And in fact, this is the best fit value of omega matter h squared in this model space, right? It goes right through here. And so it's this still having this, you can think of this effectively as having this constraint on omega matter h squared from this radiation driving effect combined with this constraint on omega matter from DESI. So it's actually DESI. DESI has a significant influence on not allowing earlier recombination.
Sorry, I have a question. I mean, I was intrigued about your suggestion about primordial black hole, primordial magnetic field. Sorry. So, what can you elaborate on what tests one can do to check that further? You know, what are there other imprints in the CMB that one could be looking for, that sort of thing?
For what thing? Sorry, I missed it.
Primordial magnetic fields.
Oh, magnetic fields.
Yes.
Right. So, if these really are modifying recombination in the way that is helpful for concordance, then you're modifying how the mean free path is changing with time, and how that mean free path is changing with time relative to the expansion rate. That ratio is, the data are really sensitive to it, and as we go out to higher and higher at L, we're probing. We effectively are probing earlier and earlier epochs in recombination when the mean free path is getting smaller and smaller. Both with just how diffusion is impacting the spectra, damping it down, and also with polarization generation. Making precise measurements at even higher values of L, you start to see differences with lambda CDM. So here's the MODREC, best fit. This isn't with the DESI data. This is before the DESI data. But this is typical that we're seeing significant departures. If you manage to agree with lambda CDM and a higher Hubble constant in the data that's down here, on the left panel we're showing the current data. And so these curves are all consistent with current data for these alternative models, including the modified recombination model. And then these are the error bars we expect to get out of our 10,000 square degrees survey. And here's in the TE correlation function, temperature, polarization, correlation. And actually, even this is detectable in the E-mode polarization power spectrum.
So I'm just guessing in terms of, okay, there are no other ways to check this, like for example, people look for the intergalactic magnetic fields in the intergalactic medium, that sort of thing. Is there any way to place further constraints with other additional data?
I'm not sure, so I just haven't thought about that enough. Jens is, of course, well, I don't know if you know Jens or not, very interested in checking this with looking at the recombination radiation, right? So all of this is happening outside of equilibrium, chemical equilibrium between the photons and the atoms. So there are recombination lines to look at. They would certainly be altered by this, and that would be the most direct way of testing this.
Well, maybe one last comment. Okay.
So, if you go back to your plot with DESI with your modified recombination, I agree that modified recombination looks really interesting and it's really cool that DESI supports it. But I guess as a viable solution to H0, based on this plot, if you have supernovae datasets which would constrain omega matter, and recently they seem to be constraining it to higher omega matter, wouldn't you be moving in the opposite direction then?
That's right. So even in lambda CDM, there's a tension between omega matter that you're getting from BAO and from supernovae, and what we get out of this makes that tension about 0.5 sigma worse, right? And so that's another avenue for testing this scenario is with supernovae. And right now, it's an open question to me whether the systematics are controlled well enough to worry about things at that level. And that's supernova experts have confided in me that, yeah, don't worry about that too much. Anyway, that's what I've heard. But yeah, that's important.
Okay, let's thank Lloyd again.